Hello, everyone. Can you hear me?
Yes, perfect.
Okay. My name is Mingyue Zhou. I come from Huazhong University of Science and Technology. Today, I will introduce about my work detecting pulsar binary black holes with sorry. Sorry. This work is under the guidance of Anton Klein, Chris Moore, and David Girosa and Yongshao. So thank you for all the organizers for GrEAT giving me this chance to attend the Birmingham Winter School to have the chance to carry out this work. We know the stellar mass binary black holes are promising source for space gravitational wave detector LISA or TianQin. Previously, we think the threshold of SNR is 8 for space gravitational wave detector, but Chris, David, and Anton revised the threshold about 50 for 5 to 50 solar mass of stellar mass black hole. So they found the stellar mass binary black hole binaries are too quiet for LISA. We may cannot be able to detect the stellar mass binary black hole. So we wanted to know if we enlarge the message and join TianQin to find whether we can detect the stellar mass binary black hole. The O3 science run data for LIGO found there are black hole mass larger than 50. The topical event is GW 190521. The mass of one of black holes is achieved to about 85 solar mass. Kinugara showed GW 190521 may be a pulsar binary black hole. Pulsar stars are the first generation stars, and the topical mass from 10 to 100 solar mass. They will express a stable mass transfer phase during evolution. This makes the pulsar binary black holes will massive than POP3 or POP1 or POP2 binary black hole. And Kinugara through the population synthesis side find the POP3 binary black hole moderate density as a function of primary mass M1. Consistent with the result of GWTC2 for LIGO at high mass range. They both have the peak at 30 to 40 solar mass. Based on this, we want to research whether space gravitational wave detector can detect the pulsar binary black holes. The first part of this work is to calculate the threshold of SNR. The threshold of SNR depends on the number of templates. For stellar mass binary black holes, template bank is how many templates we need to place to cover the whole gravitational wave parameter space. The number of templates depend on the distance for two nearby templates. Phasor matrix represent the distance for two nearby templates. So we can integrate over the parameter space for square root of determinant tau to obtain the template bank. Here we consider an eccentric precessing waveform, and Sn represent the PSD for GW detector. The parameter including the mass for black hole reach of 5 to 100 solar mass, and the multi-time from 0 to 10 years. Then here, I will introduce the relationship between SNR and the number of templates. We define the detection statistics as the phase maximized inner product between the data S and the template. When the data only include the noise, the sigma alpha satisfies the distribution. When there is a gravitational signal, sigma alpha satisfies the distribution, satisfies the rest distribution. We assume when sigma alpha larger than sigma threshold, we think we detect the signal. The first alarm probability PF is this part. Then we can obtain the relationship between PF and the sigma threshold. And also through the detection probability, we can obtain the relationship between SNR and the sigma threshold. Combine this, we obtain the relationship between N-bank and the SNR. For joint detection, PF is the square root of individual detection, so the threshold of SNR will lower for joint detection. So calculating the number of N-bank, we obtain the threshold of SNR for LISA and TianQin. We find the threshold of TianQin is about 15.6. It is close to LISA 15.4. And when we join LISA and TianQin, we find the threshold of SNR is about 11.4. Now I will introduce the detection number of POP3 binary black hole. So population synthesized, can you give us obtain the POP3 binary black hole mass model? This figure is a primary mass M1 distribution. This figure is a mass ratio. Then we can calculate the SNR for binary black hole mass satisfy this distribution. So simulation, we obtain the histogram of SNR distribution. This is the passive energy view. We find almost cannot detect the source for individual detection, but the joint detection can find about 13 sources for LISA and TianQin. So summary, the threshold of SNR for TianQin is about 15.6. It is close to LISA 15.4. And joint SNR threshold about 11.4 for LISA and TianQin. And it is almost impossible for an individual space gravitational wave detector to detect the POP3 binary black holes. But the detector network will detect about 13 POP3 binary black holes. That's all. Thank you for all your attention.
Thank you very much. Are there any questions for Mingyue? So maybe no one's asking right now, I'll ask a question. So how accurate, or what's the, I guess, percentage of accuracy for that SNR?
Sorry, my English may be poor. Can you pardon your question?
Yeah, so normally you have you know, with any calculation, there's always an error, a percentage of it that is just the error of the calculation. So what's the error in that value, or how accurate is SNR? Because obviously there's what you expect, and then the reality once, you know, things are actually working and you can actually measure things. So what's the error in the calculations?
Here is a preliminary result. So there are only one run. So maybe I cannot give the error.
So Mingyue, actually the question is about the uncertainty when you're calculating the signal noise ratio threshold. 那个计算信噪比的那个误差或者是不确定度来自哪些？有多少？
计算信噪比的不确定度。
Yeah. So how you calculate the signal noise ratio threshold, and what is potential uncertainty or error in that calculation? I think maybe that directly connected with the number of templates you found based on your facial information metrics. That error maybe can going in from there.
If you know the answer, it's okay. I think Martin has another question, so maybe we'll let Martin ask the question just because we don't want to overrun in time. So Martin, the floor is yours.
Yeah, sure, no problem. Thank you, Mingyue, a very nice talk. My question, I'm sorry if I maybe missed this. Forgive me if you already explained this, but one of the possibilities for TianQin is that there will be a 1 and 2 constellation to avoid any downtime of the instrument. So basically, when TianQin 1 is not taking data, TianQin 2 will be. So my question is, could we expect then that the number of detections would be approximately 2 times greater if there is TianQin 1 and TianQin 2 operating with LISA?
Here I only consider the TianQin 1, not consider the TianQin 2.
Yeah, absolutely. I understand. And I know you haven't done the calculations. I am just asking do you expect that if there is TianQin 1 and TianQin 2, the number of sources should be approximately twice, because that way there will be a constellation of 2 satellites operating all of the time?
Yeah, maybe we jump the TianQin 2, the SNR will be increased about squared 2.
Okay, no, this is good. That's what I was wondering. I was wondering if there would be an additional benefit from TianQin 1 and TianQin 2 because the SNR would be higher, or if just you would avoid the gaps. It's okay, we can talk about it some other time, but thank you.
Okay.
Are there any other questions?
I have a quick question, but I don't want to hold things up too much.
If it's a very quick question, go for it.
I was just going to ask about whether you have been able to check how accurate the Fisher matrix approach is for these events, comparing, like, because you're approximating for each event the posterior distribution of the parameters based on the Fisher matrix, but this is often very SNR dependent, and quite an important part of the problem that you're trying to diagnose is that the events are low SNR, which is where that approximation can break down. So I wondered if you had been able to check how accurate that approximation is for the individual events.
Yes, I think actually, as a collaborator of this work, I think it's a good comments, especially for the low, relatively low signal noise ratio of these stellar mass black holes. Fisher matrix maybe has some systematic underestimate of these errors. So maybe there is some, as Maricela was asking, maybe uncertainty or errors that is actually a possible, it's very important maybe source that going into this calculation. I don't know if whether or not Mingyue has mentioned at the earlier of this work, he was actually doing this calculation, especially the signal noise ratio part, based on the work when she was started, when she was visiting students in Birmingham, late 2016 also. So she was grabbing the code from Antoine Klein and Chris Moore et al. to do the calculation, and she was modify the orbits and response of this detector from LISA to TianQin.
Okay, thank you.
Okay.
Thank you.
I have a question. Okay.
Shuai, is it okay if we let your question for the end, just to make sure that we have enough time for all the talks, if that's okay?
Okay.
Thank you. Sorry. So I think we should all thank Mingyue, and we should let Leigh go next. So.
Sorry, 1 sec. I just need to adjust my screen.
Yeah. We now have Leigh Smith from Glasgow University, and she'll be talking about the search sensitivity of gravitational waves from parabolic black hole capture events. So we'll let her start.
Yeah, hi. So I'm going to talk about a study that was carried out on search sensitivity of gravitational waves from parabolic black hole events. This was carried out by myself and several colleagues from Glasgow, Zurich, and Korea. Just to give a brief overview of what I'll speak about, I'll cover the basics of binary black hole formation before concentrating a bit more on close black hole encounters, which is the events that are considered in the study, and give some differences between what a capture and flyby event is. Then I'll talk about the simulated waveforms we used before covering the analysis we carried out to get the search sensitivity results, and I'll just give a few of our future plans after that. So LIGO have detected many events so far, but the majority of these have been binary black holes, which are seen as all the blue dots in this plot. Binary black holes can be formed through various mechanisms, which all lead to different source properties. And one of the source properties that is interesting to look at is eccentricity, because it can give us clues as to which formation channel is responsible for all these black holes. There's two main formation channels. The first one is isolated binary formation, in which the two objects normally form a binary before they become black holes. And these types of formation have very long timescales, meaning that their orbits have time to circularize before they merge. and hence they have very low eccentricities most of the time. Whereas the other main formation channel is the dynamical evolution, in which the two objects normally form a binary when they're both already black holes. And these normally occur in very dense environments, which there's a variety of ways in which this can bring up the eccentricity of the orbit. It's not promised that dynamical evolution will always produce an eccentric orbit, but it is much more likely. So one form of dynamical formations interesting is close black hole encounters, because these are very likely to produce high eccentric orbits. These normally occur in galactic nuclei and globular clusters by single-single and binary single interactions. And during this event, two black holes pass by each other and interact, and they can either produce a flyby event or a radiation-driven capture event. So in a capture event, the black holes lose enough energy to become bound, and they merge very quickly before the orbit can circularize, which means they will have a very high eccentricity. Otherwise, the flyby, the two black holes will interact with each other, but they'll continue off in separate paths, which will still give a gravitational wave signal, except it'll have a different signal morphology to the capture events. So during this event, energy is lost from the system in the form of gravitational waves. And this decides whether the black hole encounter will produce a capture event or a flyby event based on a threshold of this radiated energy. So for a capture event to occur, we need the radiated energy in gravitational waves to be greater than the initial orbital energy. And you can see some examples of these thresholds for various mass ratios in this plot here. So we have all the points on the right-hand side of the dotted line represent a flyby event, while all the dots on the left-hand side, including the point on the boundary, represent a capture event. And you can see these vary for values of initial angular momentum. It's worth noting that the events near this boundary will emit the most gravitational waves, which makes them interesting to us. And also on the capture side, near the boundary, there is a special type of event where the two black holes can interact with each other more than once before they actually become bound. And it gives the waveform this double blip structure, which I'll show you later on in one of the other slides. So the waveforms used in the study were simulated through numerical relativity by Yongbok Bae and his colleagues in Korea. It's important that numerical relativity was used for this due to large relative velocities that occur in these events, and it also often creates strong field dynamics at small orbital separations. Numerical calculations and numerical relativity calculations are very complicated though, and in order to make them a bit more simple, they've assumed a parabolic approximation, which means that they can say a weakly hyperbolic orbit is approximately the same as a parabolic orbit, and so they could reduce their parameter space for the calculations. So we did have capture and flyby waveforms available to us. However, we decided to just concentrate on the capture ones just now. And I'll show you these here. So this is an example of all our waveforms for a total mass of 100 solar masses. You can see that it varies over 4 mass ratio values, and each mass ratio value has 2 waveforms, one with a high angular momentum value and one with a lower one, which will be a weaker signal. And you can also see the double blip structure that I was talking about earlier for the mass ratio 2 waveforms, where the black holes have had a small interaction and separated again before they've actually interacted for a second time and become bound. So these waveforms were rescaled to total masses of 10, 50, 100, and 200 solar masses, which gave us quite a lot of waveforms. These were injected into the coherent wave burst algorithm, which is an unmodeled search algorithm that relies on the excess coherent energy to detect a signal rather than relying on a bank of template waveforms that most modeled search algorithms, such as matched filtering methods, would require. We have set the settings to match the second observing run, which basically means we're evaluating the sensitive distance to these events during O2. So CWB can output many things. Here's an example of a likelihood time frequency map for the double blip waveform I showed you in the last slide, and you can see the two bits of signal being picked up here. But what was most important to us is that the output, the detection of efficiency as a function of root sum square strain for each waveform. And an example of this for one of the waveforms is seen down here. So these values had to be converted into units of distance in parsecs before being the sensitive volume could be calculated. Okay, so the results, this is the results. These are shown just for the high angular momentum waveforms. And the plot basically shows the sensitive distance for a variety of total mass and mass ratio values. You can see that the values of higher mass can be detected out to much further than the lower mass waveforms. And there's also a trend where a mass ratio of 1 is more detectable than the higher mass ratios down the bottom. Overall, you can estimate that the events detected approximately 1 gigaparsecs. However, it is notable that some have a sensitive range about 2 orders of magnitude lower than this. And it's also worth noting that these are purely Euclidean results, and we've not yet taken into account cosmological redshift corrections, which will alter these distances slightly. And another plot here, just to show the difference between the high and low angular momentum waveforms. So this is a comparison of the detectable distance for both the high and low angular momentum. A higher percentage represents how much further we can detect the higher angular momentum value for the set of mass ratio and total mass parameters. And in general, you can see that systems with a larger initial angular momentum can be detected much further out than the lower angular momentum waveforms can. This is good though, because we expect this. As I said earlier, the higher angular momentum values are closer to the boundary between flyby and capture, which means they're emitting more gravitational waves. The only waveforms that don't seem to follow this trend are the mass ratio 2 waveforms. This potentially could be due to their double blip structure, just since they have a different morphology, they're technically a different type of event. Or also it could be the fact that the 2 waveforms chosen for mass ratio had angular momentum values very close together. So potentially could separate those a bit more and see if there's a more noticeable difference. Yeah, so to conclude, we can say that CWB is sensitive to parabolic radiation capture events, and we can expect to see these out to approximately 1 gigaparsecs with an inverse false alarm rate of 1 year. Although we expect results to change slightly after more corrections. We're currently writing a paper to publish our results in full. And for the future, there's a possibility of looking for these events in the 4th observing run, which is coming up next year. And we also plan to extend this work to the flyby waveforms that were provided in Youngbok's work as well. And at some point in the future, there's also the possibility of carrying out similar sensitivity searches on hyperbolic waveforms, since these haven't been studied in great detail either. That's me. Any questions?
I think, first of all, thank you so much for your talk, Leigh. That was very interesting. And like she said, are there any questions for Leigh?
I have a question.
Yeah.
Yeah. I was just going to ask if you, I mean, obviously you haven't, this search hasn't been done yet for hyperbolic waveforms. That's the whole point of it being future work. But if you had to kind of have an estimate of how that would look compared to the results of this, what would you say?
I honestly cannot tell you right now. I could probably look into it and get an answer, but off the top of my head, I'm afraid
No, that's fair enough. I was
they're
just wondering what kind of effects it would have.
Probably quite similar values, but it's because they are quite similar events, but yeah, they'd obviously change a bit. I can't, off the top of my head, I'm not sure if it'd be higher or lower, but I can get back to you with an answer if I find one.
Yeah, cool. Okay.
I think, Garvin, you have your hand raised, so go ahead.
Yeah, thanks. Yeah, thanks, Leigh. Great talk. I'm just wondering more about the double blip structure. So, is there an easy or analytical way to understand the time difference between the first and second blip? Like, for example, could the time difference be expressed in terms of, say, the average period of the orbital binary going around each other?
I'm sorry, I'm not really sure how. I'm not really sure how to go about. I would go about that, I'm afraid.
Yeah, that's fine. So I guess a related question is, if you were to say take a Fourier transform of what we have here, you might expect to see peaks near the orbital frequency, or twice the orbital frequency of the binary, I think. And then we would see another peak at much lower frequencies, which may correspond to the double peak. Is there any sort of relation between those frequencies?
I actually have been looking into this recently, although I don't quite have the Fourier transform for the double blip waveforms looking good yet. There are multiple peaks, but there's actually too many peaks when I do the Fourier transform.
That's fine.
Yeah, I haven't quite got to the bottom of that one yet.
Okay, Martin, I think you're next in the questions.
Yeah, sure. Thanks, Leigh. Nice talk. I just wanted to check something about what you mentioned about the cosmological corrections. So you said that you use just Euclidean distances. So yeah, that might change the distances somewhat when you include the effect of cosmology. But did you still? Is it just the distances that have still to be sort of handled beyond Euclidean?
Sorry, Martin. You went off. Your sound went off a bit for me there. I missed the middle of your question.
Sorry, I've maybe got a bad connection. I'll try and be real quick. So I'm just asking about the analysis and it being Euclidean. So I get that. That's fine. It'll be interesting to see what effect, including the cosmological distances has. But I wanted to check, are you already using the redshifting of the waveform in the analysis? So is that already included? It's just the distances that aren't treated as cosmological.
As far as I'm aware, no. Redshift hasn't been taken into account until yet, but.
Okay. Okay. So it's not just that the distances will be tweaked, but possibly, you know, the frequency distribution of the radiation will also shift a little bit because of the effect of the redshift. I see. Thanks.
No problem.
Are there any more questions for Leigh? Okay, I have one. So is there an expectation in how large a signal we get, or whether it would be larger if it's from a sort of capture event to a flyby, or the size of the signal wouldn't really be at all determined by that? It's always by the mass and stuff. Or is there any effect in whether it's a capture or flyby event?
I think mostly it relies on the properties like mass and mass ratio. The flyby events have a totally different signal structure. They more look like a sound Gaussian kind of shape. But I think the overall strain amplitudes are pretty similar between the two events. Obviously, there will be some differences, but nothing noticeable.
Okay, thank you. Are there any other questions for Leigh? No. Okay, then I think we should all thank Leigh and let Shuai do his talk. So I'll let him share his screen.
Okay. I will share my.
So he comes from SYSU, and his talk will be on the Science with TianQin Observatory, talking on preliminary results. Preliminary results on stellar mass binary black holes. So take it away.
Okay. Hello everyone. I'm Shuai Liu, who are a postdoctor from Yat-sen University. My report is about the study on the capability for detection of stellar mass black holes with TianQin. The report is based on this paper. There are 4 parts in this report. In the first, I will introduce the background. Before stellar mass binary black holes are observed by LIGO and Virgo, one finds that the stellar mass black holes in X-ray binaries are light, as shown in the purple balls. Most of the stellar mass black holes observed by LIGO and Virgo are heavier, as shown in the blue balls. Most of them are heavier than 20 solar mass. 20 solar mass. Stellar mass black holes emit gravitational waves. Susanna posted that multiband observation for stellar mass black holes in 2016, as shown in the figure. The gravitational waves from some massive stellar mass black holes can be detected by LISA before they enter the LIGO band. In this paper, Susanna about the two mass distributions, the power law and the flagging log. There are two main conclusions. One first is LISA could resolve stellar mass black holes about 10 to 3. LISA also could measure the parameters of stellar mass black holes with margin in several years. The precision is well. For example, the precision of model time and sky localization is about and 0.1 square degree respectively. Then in this after this paper, there are a series of related works. The first one is on the capability of detection for stellar mass black holes. For example, ELISA or LISA, pre-disaggregate or disaggregate. The second one is distinguish the formation channel of stellar black holes. For example, can measure the orbital eccentricity and interpret of center of mass accelerations on GW. The last one is to constrain the cosmology and testing GR. At the same time, China also proposed a spaceborne gravitational wave detection project. TianQin consists of three satellites orbiting around the Earth. The arm length is about 117,000 kilometers. The normal vector of the orbital plane points to the double wide dwarf G0806. Okay. There are three satellites from one constellation. We call it because this constellation in some as shown in the figure will be greatly affected by sunlight. We adopt 3 months on and plus 3 months off observations scenario. So if the operation period of TianQin is 5 years, the effector observation time is 2.5 years. After that, two constellations, TianQin 1+2 is also proposed. The orbital plan of the second constellation is right to the orbital plan of the original constellation. These two constellations observe alternatively, so the effector observation time becomes 5 years. The sense with TianQin includes astronomy, cosmology, and fundamental physics. The astronomy includes the stellar mass black holes, the gravitational waves from stellar black holes, TianQin band, as shown in the figure. In the second part, I will introduce the methods. In our work, we adopt 5 mass distributions: model, flattening log, and power law, and A, B, and C. This figure is showing the M1 distribution, and the rest figure is the moderate distribution. We can generate the catalog of stellar mass black holes depending on these distributions. When the gravitational the theater will respond. The response signals in the time domain are expressed as the product of waveform and a response function in time domain, but but we use to transform the response signal in time domain to response signal in frequency domain by Fourier transform. The response signal in frequency is expression. Here we adopt the 3PN waveform. Given a detector, the strength of signal detected can be characterized by SNR. For one detector across the square root of inner product of response signal. The definition of inner product is as follows. Where SNF is the power spectral density of a detector. Okay. Now we can conclude the SNR of all sources in the catalog, and the detection number is the number of sources with SNR larger than 1 threshold. You see. Next, we use the facial information matrix to estimate the parameters precision. In the case with high enough SNR, the distribution of parameters errors follow the Gauss distribution. Gamma AB is the facial matrix, and the precision is this expression where gamma 10 to minus 1 is the inner matrix of facial matrix. Now we can use the facial matrix to conclude the precision of parameters of source with SNR larger than threshold. You see, and we obtain the precision distribution. In the second part, I will show the main results. We assume the observation periods of TianQin and LISA are 5 years and 4 years respectively, as shown in the figures. In the case with SNR threshold of 5, the total number is from several to depending on different mass ratio. Depending on different mass models, even if the SNR increases to 8 or 12, TianQin also could detect several from several to dozens stellar mass black holes. Because we are more interested in the multiband source. The multiband source is stellar mass black holes with merger time less than 5 years. So this figure shows the detection number for the multi-band source. Okay. For the multi-band source, TianQin could detect the several multi-band stellar mass black holes. This figure shows the precision of parameters. We use the facial matrix to estimate the source with merger time less than 5 years and SNR larger than 8 from model C. We can see that the merger time and the sky location and other parameters, the precision is well. For example, the merger time, the precision of merger time is about 1 second. The relative errors of triple mass is about 10 to minus 7, and the luminosity, the relative precision is is about 0.1. We also conclude the precision improvement compared to LISA alone for the same stellar mass black holes. TianQin plus LISA and TianQin 1 plus 1 plus LISA could improve the precision of parameters from several to about 10. In the last part, I will give a simple summary. Firstly, TianQin could detect from several to dozens of stellar. TianQin could provide from the GWs and possible electromagnetic observation because the merger time, because the precision of merger time and the scalar quotient is about 1 second and 1 square degrees. TianQin also could distinguish formation channels by measuring the eccentricity. TianQin also has the partition to distance. TianQin could accurately measure the stellar mass black holes masses. The last, TianQin plus LISA could improve the Yat-sen number and parameters estimation precision by several times compared to LISA. Okay, thanks for your attention.
Thank you very much. Do we have any questions? Any questions? First, Shuai? Maybe if not, while people are figuring out what questions they might have. I do have a question. So you talk about which I guess Martin kind of mentioned at the beginning as well, when he was asking Mingyue about the two constellation setup. But the slide that you had, unless I misread it or misunderstood, you essentially have two scenarios. So one constellation or two constellations. So is it one or the other, or are both setups going to be operational?
Okay. I think when the constant one is operation, the constellation two is don't operation, and when the constellation two operation, the constellation one doesn't. Okay.
Sorry. So.
Oh, sorry. Oh,
my
sorry.
question is more of, so in once TianQin's running, is it always going to be either one constellation, so where you have 3 months on and 3 months off, or the two constellations where they observe alternatively, so they're never both at the same time running?
No, I think you asked the, I'm not sure whether you asked the observation centennials of the two or maybe others. Can you speak again? I'm not sure. I'm not sure I understand your question.
So my question is, in the slide, you have the observation scenario where you have a one constellation or a two constellation. So I'm wondering whether it's and so so both setups will be running, so with the one constellation and the two constellation, or is it that you'll have the one constellation setup or the two constellations, so one or the other rather than both setups, if that makes sense?
Okay. I think I consider the the one constellation and the two constellations. Okay, TianQin is one constellation, and the TianQin 1 plus 2 is the two constellations. We consider both.
Okay. I think, sorry, Garvin has his hand raised, so I'll let him ask a question now.
So it is kind of on a related question, actually. It might help clarify the question. So is TianQin going to be 3 satellites that go up, or is it going to be 6 satellites that go up?
Okay. TianQin 1 constellation, 3 satellites, and TianQin 1 plus 2 also 2 constellations have 6 satellites.
Right. Okay. So they're not going to, so for constellation 2, they're not going to take the 3 existing spacecraft or satellites and kind of move them. They're actually going to have 6 physical satellites up in space.
Yes, I think. Okay.
If,
yes, I think so.
If that's the case, in the diagram at the top, if you look at, say, 4 corners, then you would always get 3 satellites observing. However, on the diagonals at 45 degrees, you could possibly have all 6 observing at the same time, right?
Okay. Okay. I'm not sure. I'm not sure the 6 satellites could operation, but I think but I think is probably okay. I don't think. I think it's. I think it's.
I think your internet has dropped, unless it's just me.
No, his face is frozen, I think.
It's frozen.
So Gavin, as I understand, the 2 set of constellations of TianQin, which called TianQin 1 and the TianQin 2, each constellation actually is orthogonal to each other. And they don't share, I mean, these 2 satellites, these 2 formation or constellation have their own light passes, so they don't really share that. And when you operate in one of the TianQin constellation, the other will be sort of in a zombie mode because of the shining of the sun will increase a lot of thermal instability, and also some of the sunlight will blend into your light path, so cause your measurement errors. So that's why they designed these 2 constellations, so that TianQin 1 and 2 as a whole can be in operation at any moment of time of year. Yeah, that's what I understand.
Right. Oh, okay. Thank you. I think that clarifies things. Mm-hmm. So it's mainly the sun which is the issue.
Sorry, was that? So thermal is one major issue because of the illumination of the light will be in some side area of the spacecraft, not really uniformly on one side of which is actually formed by the solar panel, I guess. But when it's at some certain phase of the orbit, the sunlight will be illuminates part of the side area, So that increase some thermal things, thermal instabilities, some temperature gradients inside the instruments, inside the payload of the spacecraft.
All right, okay, that's great. Thanks.
You're welcome.
Yeah, thank you, Yan, for answering the question. I think if there's not any more questions.
Mariella, you muted yourself.
Yeah, sorry, I don't know what happened. So I think because of the time, if there's no more urgent questions, we should thank all the speakers. So thank you to Mingyue, Leigh, and Shuai, who's not here anymore, although his image is still here. So thank you very much for the talks. They were very interesting, very enlightening. And I think if there's any more questions for people, we can always email them across. So feel free to send emails across. And I'll be uploading the talks on our YouTube and our YouTube channel.